Welcome to the glass plate. In this example we're going to take a look at what happens to water flowing around in houses in colder climates during winter time. That water is hot and runs in a central system. Part of it goes through, say, copper tubes. And as the water is hot, in principle the water will cool down in these tubes, and the question is that a lot? Should we insulate these tubing or is it negligible? And we're going to do that by estimating rather than by completely solving. And that is a very important key part of transport phenomena. Are you able to do back of an envelope calculations that give you the ballpark numbers? They will not be 100% accurate, but they tell you whether things are big or small, important or unimportant. And we're going to do that here by looking at part of such a copper pipe. That pipe has a length L, say 2 meters. It has a diameter D of say 2 centimeters, and it has a wall thickness delta of about 2 millimeters. Through that water is flowing at a temperature T inlet of about 60 degrees at a flow rate phi sub v of 0.2 liters per second. The material is of copper, so the conductivity here, lambda of copper, is pretty high, is a good conductor, 400 watt per meter Kelvin. And this is what we need to try and estimate what happens here once it's been flowing through. Is it still close to 60 degrees, or are we down to 40 or 30? And did we lose an awful lot of heat in a part of the house or building that we don't want to? How do you do that if you can only make estimates and not a full solution? That goes by order of magnitude arguing. First thing, of course, to note is that the standard approach after drawing is realizing this is about temperature in and out of a system, the tube, of the water flowing, and that calls for a heat balance. And I'm going to do that in a steady state. Energy in the form of heat, internal energy is flowing in. That is the volume flow rate times rho Cp T in of water. That comes in here. Same amount of water goes out, but not necessarily at the same temperature. And it is this temperature that I need to estimate. And why is that so? Well, there may be a heat loss here, which I can write according to Newton's cooling law as A times U times some estimate of the temperature, and I'll call that T average minus T of the surrounding. Right, this is still generic. Now I'm going to assume first that there is no external heat resistance. All heat resistance comes from the copper. That's a worst case. And then I deal with, okay, this is a kind of a curved wall, heat is going through it, but the wall is relatively thin compared to the curvature, to the diameter of the tube. So for a first estimate I can do as if this is a thin flat plate. And thus U is then estimated as lambda of copper over the thickness delta, the thickness of the wall. Fair enough. But the problem is that I need to find T out, and I have an unknown T average that is a measure of the temperature inside. Now I can do two things. I can try and solve it completely, or I can say, well, I lose most heat if this is highest compared to that one. So I pretend, just for the estimate, that it is at the same temperature of the inlet. So I assume that there is little or no heat loss, and I back out whether then the temperature out is indeed very close to 60 degrees. If not, then my starting assumption that this is 60 degrees, so that overall 60 degrees, is wrong. Okay, let's just do that. We assume that T here is about 60 degrees. Out of this equation, I can now easily back out the outgoing temperature, because these are known if I estimate that one. But that is not too difficult. This is inside a house. In wintertime, well, we would like to have it around 20 degrees Celsius, isn't it? So the driving force is set to its maximum, 40 degrees. I can compute T out of that because I know this one, that is just given. Rho and Cp of water I know or can look up, 1000 kilogram per cube, 4200 joule per kilogram Kelvin for Cp. A is the area of the wall of the tube itself thus is pi d times the length. I can fill it all in, compute T out, and much to my surprise, I arrive at a nonsense answers. If this describes the heat loss, then the water would lose so much heat that it is at minus 180 degrees Celsius at the outflow, deeply frozen. So my starting assumptions must be wrong. What is the shaky one? All these is quite okay. The shaky one is when I made this the entire resistance, my estimate of T average as a measure of the temperature. Okay, I can make a better one. I now see that this must cool down substantially. Can I get away with saying, well, it is 40 degrees at the end. It loses 20 degrees and cools down substantially. Even if that I do that and fill in, I arrive at frozen water. So the conclusion is, this water will cool down really substantially, pretty close to 20 degrees, if this is the picture. And if this is the picture, you better insulate the tube, because all heat is gone in the first 2 meters. You never warm up the rest of the house. Okay, but before I start insulating, I need to rethink this. What is the other assumption? The other assumption is sitting here. I assume that the total heat loss is governed by the conductivity, the heat transfer of the tube wall. And that may not be the case. And actually, I doubt it. This is a very good conductor. But then you need to get the heat out into the surroundings, so there must be something like an external. And that is in the air. And air is a bad conductor, so that may not be very big. The U is very big. So now I need to redo this and think, what if there's an external one, and that is of the order of 10 watt per meter square, a typical value that you encounter in practice for these type of systems. Something that you cannot know, I give it in this example. What will be the consequence? Will we still have to insulate or not? Okay, let's see whether we can estimate what now is the outflowing temperature. What changes here? Yeah, basically U, and thus consequently potentially this one. For that U, it's not so difficult, because there are now two, an external plus 1 over the H of the copper wall, which I know. The very good conductor coming from a not so good conductor, you can just do the math here, fill this number in, and you will thus see that this is by and large dictated by the external, which is much smaller than the H of the copper. Thus, instead of using U estimated as delta copper over thickness of the wall of the copper tube, I now can do U is about the external coefficient that is given, 10. And I can redo that. And I start this one up, now in black. Again, worst case, my T for the driving force stays high. So I assume that the loss is negligible, that I find the maximum amount of heat lost. And what did I see? T out is going to be larger than 95.9 degrees. It doesn't cool down very much. You don't need to insulate your copper pipes. The heat loss over these 2 meters is very small, thanks to the air, which is basically a very poor conductor and the little bit of flow that is generated, making this number 10 watt per meter square Kelvin. Nothing to worry about. You can do it. You will still save energy, but it's very little. This is a difficult example. Not if you follow what I do, but for yourself trying and doing that. And try and play with it. See how I make these estimates and how I draw conclusions. If you master this, this is very, very powerful. And actually, many of the transport phenomena problems that you will encounter and will solve first starts with this. I need to know where resistances are. I need to understand what the bigger picture is going to be. Then I go to the details. Good luck.